Hi guys, we're going to talk about buoyancy. So if you recall, buoyancy is a force that acts on a partially or fully submerged body, and it's equal to the weight of water displaced by the body, or the weight of the fluid displaced, I should say. So here is a cartoon of a body, and it's displacing this amount of water here, as you can see. And there's a buoyancy force, FB, and it acts upward. It's located at the point B there, which represents the center of pressure or the center of buoyancy. So we can calculate the buoyancy force as the mass of the displaced liquid times gravity. Another way to write that in terms of the thermodynamic variables is the density of the fluid times the displaced volume, and that would be the mass of the displaced volume. So mass times gravity then would be the weight. Now this force acts through the CG of the displaced body or the displaced fluid, so that's just this light pink area here. So what I'm saying is this buoyancy force B, or the location I should say, is the centroid of that displaced fluid. Now this is in contrast to the weight of the body, which is the total mass of this body here, times gravity, or the density of the body times the total volume. And of course, that acts through the CG of the total body. So there's the center of gravity and the weight, the vector there. So this was theorized by Archimedes, 1,500 plus years ago. Let's use this to solve this simple problem. Here we have a balloon that's completely submerged in atmospheric air. The balloon has been pressurized up to 135 kPa, and it's at 20 degrees C. The mass of the balloon, the skin, is 85 grams per meter cubed. What's the tension in the mooring line? Well, the way forward would be to sum forces and sum the forces up. Now, since this is a static situation, we're assuming that the acceleration is zero. So we got 0 equals the sum of the forces. So I have the buoyancy force that acts up, and given that this is a sphere that's completely submerged, that would mean that the centroid of that displaced fluid is also the center of the sphere. So it acts then at the centroid or the center of gravity. So the center of pressure is the same as the center of gravity for this case. Then there's the weight of the balloon acting down, that's the skin of the balloon, plus the weight of the helium inside, we have to include that. And then finally, the tension of the mooring line, which I'm thinking of as pulling down on the balloon, so I've got it drawn downward. So if I plug in the variables associated with this, this is the buoyancy force, rho times displaced volume of the balloon. In this case, that's the total volume, and rho of air times gravity. And then here's the weight of the balloon, 85 grams per meter squared. So the surface area of a sphere is 4 pi r squared, minus the density of helium times the total volume of the balloon. So that's the mass of helium times gravity, that's the weight. And finally, the tension, that's what we're after. So I can rearrange this. Oh, I need to get the densities first. I know that the density of air at standard temperature and pressure is about 1.2 kilograms per meter cubed. So at a little bit higher pressure, I'm expecting the density to be slightly higher. I can calculate it by assuming that the air is an ideal gas. So I rearrange PV equals MRT, and I get P over RT. So I plug everything in there, and the R I'm using is the gas constant for air, 287 meters squared per second squared Kelvin. I get 1.61 kilograms per meter cubed. So that kind of fits with this idea that I know that the density of air is 1.2 kilograms per meter cubed. So it's a little bit more. I need the density of the helium. I can use PV equals MRT. And again, I'm using the gas constant for helium. And I get something that's quite a bit smaller that also fits with my intuition. All right, so I plug everything in and I calculate these various components, the buoyancy force, the weight of the balloon, and the helium, and I sum them all up and I get 47. So it looks like 4,700 newtons is the answer. But notice the wrong answers and how deceptive this is. If I had just assumed that the buoyancy force was equal to the mooring force, or this tension, the buoyancy force is this guy right here, 6,100. So I would have picked that. I'd have gotten the wrong answer. I would have said, hey, there's my answer, and it's wrong. Had I neglected, let's just say, the weight of the helium, that's a common mistake. That's about 1,200, 1,300 more, so then 4,700 plus 1,200 would be like 5,900 newtons. So that's that answer, neglecting the weight of the helium. And if I had neglected the balloon weight but had the helium, that would be about 260, so that would have been right over 5,000. That's what that guy is right there. So each of those answers is incorrect, but easily mistakes easily made by students. So please be careful. Anyway, try out some of the questions, and good luck. We'll see you next time.